Hi folks, welcome back to Physics with Captain Rod. I'm making this to help you out with numbers 20, 21, and 22 in your Unit 1 homework. So in number 20, let's see, there's a rock dropped from a bridge and it hits the water 8.5 seconds later. So you might want to start with a little picture here. Maybe here's my bridge and here's our person dropping the rock, and this is the water down here. So the rock accelerates down. So here's my kind of motion diagram. Now it says it hits in a time frame, a delta t of 8.5 seconds. Yours might be different because the homework is set to randomize and generate different numbers for everybody. So this is a problem about gravitational acceleration. And the acceleration due to gravity, we usually call it g, is equal to 9.8 meter per second, or 9.8 meter per second squared. So that means that after 1 second, the rock's speed will be 9.8 meter per second. And after another second, it'll be 19.6 meter per second, and so forth. Now, when you're analyzing motion like this, I strongly suggest you do it graphically. And the number one type of graph I recommend people draw is what's called a velocity graph. Right, so you're going to plot velocity on the vertical axis against time on the horizontal axis. Now initially, right here, when the rock is first dropped, it's not moving right at that instant, so the velocity is 0. So 1 point on the graph is the point 0, 0, 0 seconds and 0 meter per second. All right, 8.5 seconds later, the rock is, basically just about to hit the water, and it has some probably pretty substantial velocity to it, but we don't know a number. So we're just going to call that, I'm going to call that V final for final velocity. And then on our graph here, at 8.5 seconds, we know it's going to be moving at some speed, we just don't know what that value is. I'm going to go ahead and put it on the graph. So this height here is what we're calling V final. And then we're going to make our constant acceleration assumption, which makes this linear. Because remember, acceleration is change in velocity over change in time. And that's equal to the slope of this graph. So what that's going to allow us to do is write a couple equations here, right? So for the acceleration, we're going to use 9.8 meter per second, and that's going to equal our change in velocity over our change in time, but our change in time is given, right? 8.5 seconds. So that's going to allow you to calculate your change in velocity. Now once you have that, right, that's equal to basically, that's equal to your V final, and that's equal to this distance on the graph. So part C, where it says what is the height of the bridge, so that's going to be the change in position. In this case, it's a change in y. I'm going to go ahead and write it as a change in a height, a change in y, and that's a displacement, and that's going to come from this area right here. Hopefully you've seen my video on how to find your displacement from a velocity graph. And that's a triangle, so 1/2 base times height, and this is the base, and this is the whatever you get for this value here is your height. Once you have that, you can do part B, where it says what is the average velocity. So your average velocity, I'm going to put a bar over it because bar means average. That's going to equal your change in y over your change in t, and this is going to be your change in y, which you're going to get from this area, and the change in t is given in the problem. So that's quite a bit on that problem. I'm going to go ahead and move on here and talk about 21. Got to get rid of some stuff here first. There we go. All right, so 21, it's got a picture of a roller coaster. So you have an object here, that's going to be my roller coaster, and it's accelerating this way. So motion diagram for the roller coaster looks like this, right? So the acceleration is in this direction. And it says it's equal to 1/2 g. So what they mean by that is 1/2 of 9.8 meter per second, which is 4.9 meter per second. So this problem is very similar to 20 or to number 20. You're going to draw a velocity graph, right? Velocity against time. And although I don't see it actually stated here, but I'm sure they mean that at the starting point your velocity is 0. At your finishing point, that's going to be this dot. It's some sort of v final here that we don't know. So the first point, when time is 0, velocity is 0, goes here on the graph. Part A says, what is the roller coaster speed after 7 seconds? So the delta t here is 7 seconds. Now yours might be a different number here because, again, I set this to generate different values for different people. But what we're going to do is we're going to put this on the graph. 7 seconds. Now we don't know the v final, but it has to be something, so we're just going to put it up here somewhere. So this distance here is our v final. And then we'll make our constant acceleration assumption, right? And that means that this is linear. And then we're going to, start with our slope. Our slope, which is equal to the acceleration, is equal to change in velocity over change in time. So the acceleration is given here. The change in time is given here. That's going to allow you to calculate your change in velocity. And your change in velocity and what I'm calling your final velocity are going to be the same thing because it started with a velocity of 0. So then what you're going to know when you get the v final, you're going to know this distance on the graph. And the 7 seconds is this distance. And then the displacement, or the distance traveled, I'll call it d here this time, is this area under the graph here. So when it says how far does it travel during that time frame, you're going to get that from this area. So that's probably enough on 21. Let's move on to 22. All right, let's see. It says during takeoff, a plane goes from 0 to 86 meters per second in 7 seconds. So I'm going to write those values down. 0 to 86 meters per second in 7 seconds. Now your numbers here might be different because, again, I have this randomly generate numbers for your homework. Well, right off the bat, we can calculate the acceleration, because acceleration is change in velocity over change in time. If you go from 0 to 86 meters per second, your change in velocity here is going to be the 86 meters per second, and here's your change in time. So this now is going to be some number. It's your homework, so I'm not going to finish it or actually get a value here. It's going to be number meter per second per second. And then I would draw the velocity graph. So again, velocity on this axis, time on this axis. And at t equals 0, it's not moving. So like a lot of these problems, it goes through 0, 0. And then 7 seconds later, it's going 86 meters per second. I'm just going to put this up here somewhere. So that's going to be here on the graph, 86 meters per second. And again, we're going to make our constant acceleration assumption, which means this is a linear graph. And the 86 meters per second, that's this distance on the graph. Now let's start answering questions. Part A, what is the acceleration? Well, the acceleration is the slope, rise over run. And this is already calculated. We already calculated that earlier, so that's how you get that. For part B, how fast is it going after 4 seconds? So at 4 seconds on the graph, we're like here somewhere, and they're asking for what would this distance, be on the graph? And I would just write out, well, the slope, which is the acceleration, is equal to the change in velocity over change in time. An important fact of life here is that the acceleration is the same because this is linear. So you're going to use whatever number you have here for your acceleration. Then put in your delta t. In part B here, the one I'm looking at is for 4 seconds. Then you can calculate your change in velocity, and that will tell you how fast you're going at the 4-second mark. Part C, how fast has it traveled, or how far has it traveled by time it reaches 86 meters per second. So the 86 meters per second, going back to the original part of the problem, was after the 7 seconds. And again, the way you find displacements from a velocity graph is by area. So it's going to be this area that I'm kind of shading in blue here. And again, this is a triangle, so 1/2 base times height. So that should get you through 22. I hope you're enjoying these videos, and I hope you're enjoying the course. Have a great day.